All right, good morning, ninth grade. I hope you guys are doing well. We are going to pick up with chapter 14 in our notes. You might notice I changed the slide color from the last videos. That's because the smartboard was having some issues last time I went to record this video. So change the slide color to maybe help offset some of those issues that you won't notice them as badly anyway. We're going to try and hope for the best. We're going to pick up, this is the last section of notes for chapter 14. And we're going to talk about Earth as a magnet. Now we've looked at magnet behavior, why magnets work, how electrons affect magnets. Last week you did a paper on how they work, or you were supposed to do a paper on how they work. If you haven't done that yet, you need to get that into me ASAP, okay? And this week you're supposed to be building an electromagnet. Please be careful doing that. I hear that Isabel already burnt herself, and I'm so sorry, Isabel, that happened. Please, nobody else burn yourself. I did burn myself while I was practicing with it, but that's because I missed one of the steps on purpose. Don't do that. Follow the steps the way they're written. Do as I say, not as I do in this situation. I apologize. I should have been a better example. Anyway, moving forward. Okay, so Earth as a magnet. Now, a magnetic compass, if you guys have taken scouting at all or done any sort of wilderness survival training, you've probably done something with a magnetic compass at some point in time. But this is a device that allows a magnet to swing horizontally, so it's always pointing north. Magnets are naturally going to seek to that north pole. William Gilbert was the first to discover that a compass points north because of the Earth's magnetic field. He published his findings in his book De Magnete in 1600. William Gilbert is actually considered the father of magnetism because of all that he did with his life and the study of magnets. We're not going to get into it too much here, but he spent a large portion of his life studying magnets, their behavior, why do they work the way they do, what causes a magnet to tick. According to the law of magnetic poles, the north pole of a compass points to the magnetically south pole. So remember, opposites attract. So if a compass is seeking north, okay, it's actually, if the compass, not seeking, let me not use that word. Let me go with this word. If the compass is pointing north, then it's technically seeking the magnetic south, okay, right? Because opposites are going to attract. If it's pointing south, it's technically seeking the magnetic north. So what does that say about our Earth? Think about that. The north magnetic pole, or geographically north, is actually a south-seeking pole, or magnetically south. So even though our north pole is north, it's actually the south-seeking pole, okay? It is magnetically south. And then you have the south magnetic pole, which is geographically south, what I'm talking about here, is actually a north-seeking pole, or magnetically north. So even though we have north and we have south, when it comes to magnets, they're opposites. Okay, the north pole is actually a south magnetic pole, and the south pole is actually a north magnetic pole. Okay, so I think that's kind of cool personally, that even though you have north and south geographically, magnetically, they're opposites of each other. Okay. Declination, the angle of declination. This is the deviation that causes the compass needle to be a few degrees off from pointing to true north. This changes slightly depending on where you are at in the world. Location. All right. It does matter when you are trying to figure out where true north is on the Earth. Columbus was the first to note this on his voyage to the New World. Polaris, or the pole star, is an accurate indicator of true north. So find the North Star. Okay. And that will tell you where true north is. Isogonic lines versus agonic lines. Isogonic lines, these connect points of equal declination on the map. And agonic lines connect all points where a compass needle points to true north. If you get out, I'm trying to remember what page it is on your textbook. I can't remember off the top of my head right now. I should have looked it up before I started this video. Anyway, go to section 3 of chapter 14, and you can actually see maps with the isogonic and agonic lines on them, showing those connection points for you. Inclination. Inclination is the magnetic dip. Okay, it's the scientific term for magnetic dip. And this occurs when a dipping needle points downward towards the north-seeking pole, toward the Earth in the northern hemisphere. A dipping needle best shows inclination. So a dipping needle is a compass with a magnet free to swing vertically that reveals the angle that the lines of flux enter the Earth. And we talked about lines of flux in a previous video, but remember, lines of flux just show the direction that magnetism is flowing. Okay, so a dipping needle helps us find the direction magnetism is flowing on the Earth itself. Okay, pretend Earth is a giant magnet, and the dipping needle helps us see where those lines of flux are entering the Earth. Isoclinic lines, these are lines that connect locations having equal inclination. And then the magnetic equator is an imaginary equator that circles the Earth halfway between the two magnetic poles. It is equivalent with the actual equator, okay? But it's an imaginary line. You can't go to the equator and find a line or a stake in the ground that says, here's where the magnetic equator begins and here's where the magnetic equator ends, okay? But it is equivalent with our actual equator. The magnetosphere, now we're going to look at space, okay? How does Earth's magnetism as a whole, the fact that we have a south-seeking North Pole and we have a north-seeking South Pole, how does that affect our atmosphere when we get out into space? Okay, that's what we're going to look at with this last portion of notes here. So the magnetosphere, and hopefully you guys might remember some of this from 8th grade science last year. We did talk about space. We did briefly touch on these things, so maybe you'll remember them. If not, great time to pay attention and learn it now. So the magnetosphere, this is the extent of Earth's magnetic field in space. So think about when I drew on the board the last time, maybe 2 videos ago, to show you lines of flux and how they enter the magnet. If you remember, those lines of flux, they don't just go a little bit out of the magnet and swoop back down into the bottom of the magnet. Okay, they have the ability to really go out and reach outward, and the stronger the magnet, the more pull those lines of flux have to pull an object towards itself. Okay, the same thing is true with Earth. Okay, the lines of flux for the Earth, they have a great ability to reach out into space. Okay, so the magnetosphere is a pretty far-reaching area. Sorry, there was a bug in front of me, guys. As far as the magnetism of the Earth goes. Now, solar winds have to do with the magnetic pull of the sun and how the magnetic pull of the sun affects the magnetic pull of the Earth. All right. So these are streams of plasma, which are electrons and cations. We've talked about electrons and we've talked about cations briefly in previous chapters. You'll get more in depth with them when you get into chemistry in a couple of years. But these are streams of plasma that emanate from the sun and distort the shape of the magnetosphere. Now, ideally, lines of flux, let's pretend my water bottle's a magnet since we have it right here, okay? Ideally, lines of flux should come out from the top, circle down into the bottom, right? Ideally. Now, what happens is the solar wind is, as that line of flux comes out, it can distort it and maybe cause it to wiggle out over here and circle back down into the bottom of the Earth. Or it can cause it to go way out to the side and circle back down to the bottom of the Earth, okay? Solar wind has the ability to affect the Earth's lines of flux or the magnetic pull of the Earth. The magnetopause is the outer boundary of the magnetosphere. This is the very, very tippy top reaches of where those lines of flux stop. Sorry, I need a drink. All right, your Van Allen radiation belts. These are donut-shaped belts of high-speed charged particles. And they are the result of the magnetic field above the Earth. Now, the Van Allen radiation belts, these are pretty interesting because there was a point in time where scientists said these things exist, and the scientific community was pretty divided on it. Half of the scientists said, you're crazy, those can't even be a real thing, and the other half said, no, they are. It doesn't make sense that we have this kind of magnetic bulge that is affecting the way we rotate, the way we move in our rotation around the sun. So they came to, well, they were already in existence, but the existence of them were proven, I want to say it was in the 40s or the 50s, if I remember correctly off the top of my head. Look me up, check me out, see if I'm right on that. But you have auroras. Now, auroras, or the northern lights or the southern lights, these are the result of the magnetic field that surrounds the Earth. All right. So it's a display of shimmering lights that are the result of high-speed particles that spiral into the upper atmosphere and crash violently into molecules of air. So what happens is these high-speed charged particles, they're flying from space and they're interacting with our magnetosphere, and they cause, the way they interact with the magnetosphere, they cause these brilliant displays of lights that we call the northern lights or the southern lights, depending on which hemisphere you're in and where you're viewing the map. Oh, and that's the last one. Not a very long video. There wasn't a lot of notes to finish up this chapter. Please make sure that you're keeping up with your notes. I am going to check them for a quiz grade when school starts again. I've had a couple of you ask about the graph that you were supposed to do for your electromagnet this week. I've had some ask if it's supposed to be a line graph or a bar graph or what type of graph it's supposed to be. I'm going to give you the liberty to choose which type of graph you would like to make, either a line graph or a bar graph, one of the two, to best illustrate your findings with the electromagnet, okay? So I'm going to leave that up to your discretion, but it needs to be one of the two, line graph or bar graph. Don't get off and make something else, all right? So I hope you guys have a good day. I miss you, I'm praying for you, and I can't wait to see you guys soon. Stop. Sorry guys, I can't get it to stop.